All right, good morning. So let's get started. So today we're going to continue sort of looking at examples of applications of simplex method on different examples. All right, let's get started. So far we have seen three examples. The first one was a minimization problem. The second one was a maximization problem, or the other way around, basically. And last time we saw how the simplex method detects when there are alternate optimal solutions. So today I'm going to give you one more example. This is example number 4. This is another example of an LP problem which has alternate or multiple optimal solutions. And here is how the LP problem looks like. So we are minimizing x1 minus x2. And my constraints are minus 3x1 plus 3x2 is less than or equal to 6. Minus 4x1 plus 2x2 is less than or equal to 2. And x1 and x2 are non-negative. Okay. So once again, this is an LP problem with only two variables, so we can draw the feasible region. So let's start by doing that. Now let me start with the first constraint. So when x1 is equal to 0, x2 is equal to 2. So this is one of the intercepts. And when x2 is 0, x1 is equal to minus 2. So minus 2 is somewhere over here. So it goes through these 2 points. So this is the line corresponding to minus 3x1 plus 3x2 equals 6. Then I need to decide which side I'm going to pick. So which is the correct side? Well, the origin satisfies this inequality, so as a result, it's on the right side. So this is a region defined by the first constraint. Then let me look at the second one. If x1 is 0, x2 becomes 1. So this is one of the intercepts. Okay. And if x2 is 0, x1 is equal to minus 1 over 2. And minus 1 over 2 is somewhere over here, basically. Okay. So this is the line corresponding to the equality version of the second constraint. Once again, which side is the correct side? So, well, if you plug in 0, 0, again, it satisfies inequality. So as a result, we're going to pick the right side of this line as well. Then I have non-negative of x1 and x2. So this is these are the regions defined by my constraints. So what's the feasible region? Well, I'm going to look at the intersection of all these 4 half spaces. And if you do that, it's not too hard to see that this will be our feasible region, basically, right? So in that case, our feasible region is unbounded in some sense. So, okay, so what's the next step? So this is a minimization problem. I'm going to look at the Assoc coastline, right? So let's start by doing that. So I'm going to look at the line given by x1 minus x2 equals 0. Okay. So which is the same thing as x1 is exactly equal to x2, right? So what does that line look like? It goes through the origin. So what does the x1 equals x2 line look like? It's just a 45-degree line, right? Basically. Okay. So essentially it looks like this line right here. So this corresponds to x1 minus x2 equals 0. So this is my Assoc coastline. What is my C vector for this problem? So it's going to be 1 minus 1. And 1 minus 1 actually points in this direction. Which is perpendicular to the Assoc coastline. And what's the improving direction? So it's the negation of that. So basically, I want to push this line in the opposite direction of C as much as I can. And if I do that, what's the best I can do? So it's not too hard to see that, this line, the Assoc coastline, is actually parallel to this constraint, right? So the best I can do is actually, coincide with that constraint. And if you do that, it's not too hard to see that the optimal solution will be everything starting from here and everything on this half line, basically, right? So that's the best I can do. Question? So the slope of this line is the same as slope of this line, basically, right? So if you look at the coefficients, 1 minus 1 minus 3, 3, so they're actually proportional to one another. So as a result, you have the same slope. And if you keep pushing this line in this direction, in the direction of negative c basically, then the best you will do is coincide with this constraint. So everything on this half line will be optimal, right? So in this case, there's one basic feasible solution which is optimal. And all other optimal solutions are non-basic, basically, right? So they're not basic feasible solutions. Okay? So let's see how the simplex method actually detects this. So I'm going to start by setting up the tableau again. So once again, the first step is turn it into standard form. So that's exactly what we're going to do. I'm going to add select variable for the first and second constraints, which I'm going to call x3 and x4. Now, what does rho 0 look like for my problem? So what's the coefficient of z? Minus 1, 1. So please make sure that you negate the coefficients, right, in row 0. So everything else is 0. Then what does row 1 look like? So z is a coefficient of 0. Then I have minus 3 plus 3. And then I need a select variable for the first constraint, which is x3. So that's going to have coefficient 1. And the right-hand side value is 6, right? All right, so what about row 2? So I'm going to start with 0, then minus 4, plus 2. x4 is the select variable for the second constraint, so I'll have 0, 1. And the right-hand side value will be 2. All right, so what are my basic variables? So I always have z for row 0. What's the basic variable for row 1? So you're going to look for the second column of identity matrix. So, and x3 has that property. And then finally, x4 is the basic variable corresponding to row 2, right? All right, so what are my basic variables in this case? So they're going to be x3 and x4. And what are the current values? So x3 is equal to 6 and x4 is equal to 2, right? And what are my non-basic variables? x1 and x2, exactly. And what are their values? They're both equal to 0. And what's the value of the objective function? That's also equal to 0, right? Since x1 and x2 are 0, z is also equal to 0. Now, what's the corresponding corner point in my picture? So it's going to be the origin, basically, right? So right now, we're actually at this point. OK? This is a minimization problem. So is this an optimal solution? No, so what should I be looking for in this case? So I should be looking for a non-basic variable whose row 0 coefficient will be positive, right? Okay. And do we have such a non-basic variable? Yes, we do. x2 basically, if I increase x2, then z will decrease basically, right? So x2 will be the entering variable. And how do I determine the leaving variable? So we do a ratio test. So what's the ratio for row 1? So I'm going to take the right-hand side value and divide it by the entry underneath the entering variable, right? So if I do that, 6 divided by 3 is equal to 2, so which means that I can increase x2 up to 2 and still satisfy the first constraint. And what's the ratio for row 2? So it's going to be 2 divided by 2, and that's equal to 1. And obviously 1 is smaller than 2, so row 2 actually wins the ratio test. Okay. So what does that imply? So x4 is the leaving variable. And so what's going to be my next pivot? So basically, I'm going to look at the column of the entering variable, look at the row of the leaving variable, and the intersection is this entry, right? So now I'm going to pivot on that entry. So let's do that. Basically, in this case, x2 enters and x4 leaves. So this is my new tableau. So now essentially what I'm going to do is I'm going to try to make the column underneath x2 look exactly like the column underneath x4, right? So x2 will assume the role of x4. So which means that I'm going to first start by making the circled entry equal to 1. Okay? So how do I do that? Exactly. So I'm going to divide row 2 by 2, and if I do that, I have 0, minus 2, 1, 0, 1 over 2, and the right-hand side value is 1. Okay? So Exactly. I can multiply the new row 2 by minus 3 and add it to the previous row 1 so that this entry becomes 0. And if you do that, you end up with the following. So 0, 3, 0, 1, minus 3 over 2, and the right-hand side value is 3. And finally, I'm going to multiply the new row 2 by minus 1 and add it to old row 0. And if I do that, the entry underneath x2 in row 0 will be equal to 0. Okay? And if you do that, you end up with the following. 1, 1, 0, 0, minus 1 over 2, and the right-hand side value is minus 1. Okay? Again, just elementary row operations, so nothing too specific, basically. So z is the basic variable for row 0. What about row 1 and row 2? So now the second column of the element matrix looks underneath x3, appears underneath x3, so x3 is the variable for row 1, and similarly x2 is the basic variable for row 2. Okay? So let's just write down the basic variables again. So my basic variables are x3 and x2, and their values are equal to 3 and 1. My non-basic variables are x1 and x4. Both of them are equal to 0. And what's the objective function value for this solution? So it's going to be minus 1, basically, right? So we started with an objective function value of 0. So now we have a better objective function value of minus 1, right? Okay. What's the corresponding corner point? Well, x1 is equal to 0, x2 is equal to 1. So essentially, we move to this point now, right? Okay, so let me go back to my tableau again. So now I found a better basic feasible solution, okay, than the first one. Is this the optimal solution? No, why not? Again, we have a non-basic variable, which is x1, and it has a positive coefficient in row 0, which means that if I increase x1, then I can further decrease the objective function value, basically, right? Okay? So as a result, I'm going to try to enter x1. I'm going to try to increase the value of x1. All right, so now I'm going to apply the minimum ratio test. What's the ratio for row 1? So I'm going to divide 3 by the entry underneath the entering variable, which is 3. So I'm going to have 3 divided by 3, which is equal to 1. What about row 2? No ratio, because essentially this entry is not positive, which means that row 2 does not give me any restriction, basically, right? So we've seen this before. So there's no ratio for row 2. And since there's only one ratio, obviously that also wins the minimum ratio test. Okay? And that determines the leaving variable. So what's my leaving variable then? x3, exactly. So now x1 enters and x3 leaves. So what's my next pivot? So I'm going to again look at the column underneath the entering variable. I'm going to look at the row of the leaving variable. And this is the intersection. So now I'm going to pivot on that entry. In other words, I'm going to try to make the column underneath x1 look exactly like the column underneath x3. Okay, so x1 will take the role of x3, basically, right? All right, so let's do that quickly. So all right, so what's my first step again? So first, always try to make the circled entry equal to 1, right? That's the first step. So essentially, all you need to do is divide the circled entry by 3, or divide that row by 3. And if you do that, you end up with the following. So I'm going to have 0, 1, 0, 1 over 3, minus 1 over 3, minus 1 over 2, sorry, and right-hand side value is 1. Okay? Then I'm going to multiply new row 1 by minus 1 and add it to row 0. Okay? And if you do that, you end up with the following. You have 1, 0, 0, minus 1 over 3, 0, and the right-hand side value is minus 2. So now the objective function actually improved further. Okay? Finally, I'm going to try to make this entry equal to 0. Okay? And to do that, I'm going to multiply this row by 2 and add it to row 0. Sorry, add it to row 2, rather. And if I do that, I end up with 0, 0, 1, 2 over 3, minus 1 over 2, and the right-hand side value is 3. Okay? So let's specify our basic variables. So I have z for row 0. What's the basic variable for row 1? It's going to be x1, because x1 has the second column of the identity matrix. And x2 has the third column, so as a result, x2 will be the other basic variable. All right, so let me write down my basic variables. So they're going to be x1 and x2, and their values are 1 and 3. And my non-basic variables are x3 and x4. Their values are 0. And what's the objective function value? -2. So we actually have an even better solution now. Now, what is the corresponding corner point? So it's actually, if x1 is equal to 1 and x2 is equal to 3, it's not too hard to see that. You can compute this point easily. So you now move to this point right here. Okay? Is this the optimal solution? Well, this is an optimal solution, basically, because there are no non-basic variables with a positive coefficient. Okay? So the only non-basic variables are x3 and x4. If I increase x3, then z will actually increase, right? So I don't want to do that. On the other hand, if I increase x4, so what happens in that case? Well, basically, the value of z does not change, right? So this is pretty similar to what we had in the earlier example. So x4 is a non-basic variable, but its row 0 coefficient is equal to 0. Okay? So which means that if I try to increase the value of x4, then the objective function value will not change. Okay? But essentially what I'm going to do is I'm going to be looking at different optimal solutions, right? So that's essentially what we did last time. So now this is already an optimal solution. Okay? But, you know, as we did last time in example 3, we have a non-basic variable with a row 0 coefficient which is equal to 0. So which means that if I increase x4, that means that the objective function value will not change, basically, right? Okay? So let's try to do that. So let's try to increase x3 and see what happens. Sorry, x4 rather. So we can increase x4 without changing the objective function value. Now, what happens if I increase x4 from this solution? So I should be looking for a leaving variable, right? And what's the leaving variable in this case? Well, let me look at row 1. So what's the ratio for row 1? No ratio, because this entry is not positive, right? So basically there's no leaving variable here. What about row 2? Well, we have the same problem here as well, right? Again, there's no positive coefficient, which means that there's no leaving variable. Okay? So in other words, essentially, what does this mean? This means that I can increase the value of x4 as much as I want, and none of these two constraints will be violated, basically, right? Okay? So let me repeat it again. So basically, if I want to increase the value of x4, I can actually increase it as much as I want without violating either the first or the second constraint. Does everybody see that? Okay? So as a result, let's see what happens in that case. So we can increase the value of x4 as much as we want, without changing the optimal value. And as I said, none of the two constraints will be violated, right? I can increase the value of x4 as much as I want, and I know that if I increase x4, then the value of x1 will increase from row 1, right? And the value of x2 will also increase, which means that I will never actually have a situation where I have a negative variable. Okay? Sure. How can we decide whether it's optimal or not? You tell me.
I have a note in here. I said, since there are no negative coefficients in row 0, this basically is the solution is right or false?
Since there are no positive variables, actually, positive coefficients in row 0, this is a minimization problem. Okay? So this is a minimization problem, so that's why I'm looking for a positive coefficient in row 0, because if there's a variable with a positive coefficient, and if I increase that variable, then the objective function value will decrease in that case, okay? Okay? That's exactly what we did here, right? So x2 has a positive coefficient here. x1 has a positive coefficient here. However, here there's no positive coefficient in row 0. Okay? All right, so now let's try to understand what's going on. So I can increase the value of x4 as much as I want, and there are no leaving variables, right? So which means that I'm not going to violate constraint 1, and neither am I going to violate constraint 2. So what does that mean now? So essentially, just like we did when we sort of discussed these systems of linear equations, what I'm going to do is I'm going to try to find a parametric solution. Okay, so I'm going to let x4 be equal to a. Okay, of course a has to be a non-negative number. And then what I'm going to do is I'm going to try to figure out the values of my other basic variables as a function of a. So if I increase the value of x4, then I'm going to try to see how the values of x1 and x2 will be affected by that. Okay. So let me look at row 1. So what's the corresponding equation for row 1? Let me write it in equation form. So I'm going to have x1 plus 1 over 3x3, right? Minus 1 over 2 x4 will be equal to 1. So this is the equation form, basically, right? Okay. But I know that x3 is equal to 0. I don't want to increase that, because if I do, then the value of z will increase, and I don't want to do that. So this part will not be affected. Okay, so in other words, x3 will be equal to 0. And I know that x4 is equal to a, so which means that the value of x1 will be given by what? So it's going to be given by 1 plus 1 over 2 times a, basically, right? Okay? If a is equal to 0, then x1 is equal to 1, which is the current solution, basically. And as I increase a, then the value of x1 will also increase. Okay? So this is the reason why there's no ratio, basically, okay? So x1, you can never make x1 negative by increasing the value of x4, okay? So which means that you can never violate non-negativity constraint of x1, okay? So let's just do the same thing for row 2. Let me write down the equation form. I'm going to have x2 plus 2 over 3 x3 minus 1 over 2 x4, and the right-hand side value will be equal to 3. So once again, the value of x3 does not change. It's equal to 0. I can actually write x2 in the following way. So it's going to be 3 plus 1 over 2 times x4 is equal to a, so I'm going to set it equal to a again. Okay? So which again means that if a is equal to 0, then x2 will be equal to 3, which is the current solution. Okay? And as a increases, the value of x2 will also increase. Okay? Now let me go back to my picture. For example, if a is equal to 1, for instance, okay? If a is equal to 1, then the value of x1 will be 1 plus 1 over 2, which is 3 over 2, right? And the value of x2 will be what? So 3 plus 1 over 2, which is 7 over 2, basically, right? Now, what's the corresponding solution on this picture? Well, if you think about this a little bit, essentially, as a starts to increase, you start actually moving along this direction, okay? So essentially, as the value of a changes, you're finding all different solutions on this half line, okay? When a is equal to 0, you're exactly at this point, okay? And as the value of a increases, you're starting to move along this half line, and you know that everything on this half line is an optimal solution, right? Okay? So as a result, the reason why there's no restriction on x4 is that because you can go along this line, or half line, as much as you want, right? So there's no other constraint that sort of stops you, okay? So you can make a arbitrarily large, in which case, of course, you're going to move, far out there in that direction, okay? So for every different value of, for every different non-negative choice of a, there's going to be a corresponding solution on this half line. Does everybody see that? Okay? So once again, that's the reason why, there's no leaving variable, basically, because there's no other constraint that blocks me from going in that direction. Does everybody see that? Okay. So as a result, again, the simplex method actually gives us all possible optimal solutions, just like it did in the previous example as well. Okay. So I can write this in the following way. So therefore, for every choice of non-negative a, non-negative number a, I can simply set x1 equal to 1 plus 1 over 2a, I can set x2 to be 3 plus 1 over 2a. And then I can set x3 always equal to 0, so the value of x3 does not change. And I can set x4 to 2a, right? So basically, I have a system, or I have a set of solutions parameterized by the value a. So for every different choice of value of a, I can get a different solution, basically. Okay? So this will be an optimal solution. Does everybody see this? So, okay. So now let me write down my variables in vector form. So x1 will be equal to 1 plus 1 over 2a. x2 will be equal to 3 plus 1 over 2a. x3 will be equal to 0, and x4 will be equal to a. Okay? Then I'm going to sort of decompose it into two components. So I'm going to separate the ones that do not depend on a, and I'm going to separate the ones that do depend on a. So I can write this as 1, 3, 0, and 0. Plus, I'm going to have 1 over 2a, 1 over 2a, then 0, and I'm going to have a as well. So 1, 3, 0, 0 is essentially the same solution that we had in the last tableau. Okay, x1 is equal to 1, x2 is equal to 3, x3 and x4 are equal to 0. So this is the BFS, right? And then this is the part that depends on a, basically. Okay, so I can also write it in the following way. So 1, 3, 0, 0, I can actually factor a out. And if I do that, I have 1 over 2, 1 over 2, 0, and 1. Okay? Now, what's the point of writing it this way? Well, when a is equal to 0, we just get this basic feasible solution, right? So when a is equal to 0, I simply get x1 is equal to 1, x2 is equal to 3, x3 and x4 are equal to 0, so which is exactly the solution right here. As the value of a increases, okay, then I'm going to get different solutions, basically, for my problem. Different optimal solutions, okay? For every different choice of a, I'm going to have a corresponding optimal value. And if I look at the x1, x2 components only, so x1, x2 start at 1, 3, and they move in the direction of 1 over 2 and 1 over 2, right? So as it increases, I'm actually multiplying the value of x1, x2 by 1 over 2 times a and 1 over 2 times a, and adding it to the value of 1 and 3, okay? So if I go back to this picture again, so it tells me basically that if I start at this point, and if I move along this line, so 1 over 2 is a vector that actually sort of that's directed in this direction, okay? So basically, as I increase a, I'm actually starting to move on this line, okay? So when a is equal to 0, I'm at this point, and as a increases, I'm actually getting all possible optimal solutions. So the main message is that the simplex method actually gives you all possible optimal solutions, even if these points are not basic feasible solutions, okay? So there's only one basic feasible solution, which is found by the simplex method, but the simplex also gives you all possible other optimal solutions as well. Is that clear? Any questions? So the other thing that's important is the following. So if I go back to this solution, now for a is equal to 0, I know that I have a basic feasible solution, right? So that's the starting point of that half line, okay? But as I start increasing a from 0, then the solution is no longer a basic feasible solution. That's important, okay? Why not? Because for example, for a is equal to 1, x1 will be positive, x2 will be positive, and x4 will be positive as well. Okay? So I'm going to have actually 3 positive variables. But I know that in a basic feasible solution, I can have, when there are 2 constraints, I can have exactly 2 positive variables, right? So which means that for positive values of a, this is no longer going to be a basic feasible solution. And indeed, if you look at the picture, as soon as you start increasing the value of a, you're actually leaving this corner point, and then you never actually arrive at another corner point, okay, as you move along. Okay? So as a result, once again, the main message is the following. So the simplex method not only gives you a basic feasible solution which is optimal, but in such a case, it also tells you all possible optimal solutions as well. Okay? Is that clear? Any questions? All right. So now the last 2 examples actually show that the simplex method can find alternate optimal solutions, if there are, of course, any. The next question is the following. So what does the simplex method do if the problem is unbounded? Okay, so all the examples we have seen so far had at least one optimal solution, right? But we know that there are some LP problems which are unbounded. And if I have an unbounded LP problem, then there's no optimal solution, right? Now, the simplex method, note that, moves through the corner points of my feasible region. But the problem is that if the problem is unbounded, then there's no optimal solution, right? So the question is, can simplex method actually deal with that, okay? And if it can, how can it deal with that? So we're going to look at one such example now. This is example number 5. So now we're going to look at an example where the problem is unbounded, and we're going to see how the simplex method will perform on such an example. So suppose that we consider the following problem. I'm going to maximize x1 plus 2x2. And I have the following constraints. x1 minus x2 will be less than or equal to 10. And 2x1 will be less than or equal to 40. And x1, x2 will be non-negative. Okay? All right, so again, let me draw the feasible region, just to sort of convince you that this is indeed an unbounded problem. Let me start with the first constraint. So if x1 is 0, x2 will be equal to minus 10. Let's say minus 10 is somewhere over here. And if x2 is 0, x1 will be equal to 10. And 10 is somewhere over here. So basically, it's going to go through these 2 points. Okay? And which side of this line should I pick for the first constraint? So once again, just plug in 0, 0. So it's not too hard to see that it satisfies the constraint. So I'm going to pick this side of this line. Now, what does the second constraint look like? So 2x1 is equal to 40, right? So first, I'm going to look at the equation version. So which means that x1 is equal to 20. So what does that line look like? It's going to be a vertical line, basically, right? So, and 20 is somewhere over here. So should I pick the left side or the right side to satisfy the constraint? So just again, plug in 0, 0. Obviously, this is satisfied. So I'm going to pick everything on or to the left of this line. Then I have non-negative to x1, x2, so which means that everything should be in the first quadrant. Then my feasible region will be given by this area, basically, okay? All right, so what's the next step? Well, I'm going to look at the isoprofit line. So this is a maximization problem. So first, let's try to draw the line x1 plus 2x2 equals 0. So what does that line look like? So it's going to go through 0, 0. And I need one more point. For example, if x1 is equal to 20, x2 will be equal to minus 10, basically, right? So it's going to go through these 2 points, right? So when I said x1 plus 2x2 equals 0, if x1 is 20, x2 will be minus 10, right? To satisfy that. So it's going to go through these 2 points. So this is my isoprofit line. What's the next step? I need to figure out the improving direction. Okay, this is a maximization problem. What's the improving direction for this problem? 1, 2. So 1, 2 will be perpendicular to this line, and it's going to point in this direction. So once again, since this is a maximization problem, so the improving direction is the same as C itself. So I need to sort of push the isoprofit line in the direction of C as much as I can, right? Without leaving the feasible region. And what's the best I can do? Well, note that my feasible region actually goes in the vertical direction to infinity, right? So which means that there's nothing that stops me from going in that direction, right? I can actually take this line and I can move it in this direction as much as I can, right? So there will never be a constraint that will block me, so which implies that this problem will be unbounded, basically, right? Does everybody see that this is unbounded? So this will be an unbounded problem. So graphically, we know that there is no optimal solution. Okay, so the question now is the following. How does the simplex method find out about this, basically? Okay, so how can the simplex method tell us that indeed there's no solution? Well, let's try to see what's going on. So let's set up the tableau again. So once again, I'm going to use x3 and x4 as the slack variables for the first and second constraints. Now, what does row 0 look like? So 1, minus 1, minus 2. I'm negating the coefficients. 0, 0, right-hand side is 0. What about row 1? 1, minus 1. 1, 0, right-hand side is 10. And I'm going to have 2, 0, 0, 1, and 40, right? So this is my initial or first basic feasible solution. Okay. What are the basic variables? x3 and x4, right? So from now on, I'm not going to write down basic and non-basic separately, but you can also see it from the tableau directly. x3 and x4 are basic, and their values are 10 and 40. x1 and x2 are non-basic, their values are 0. And the right-hand side value is 0. And it's not too hard to see that this actually corresponds to the origin again, right? So the corresponding corner point is this one right here. And indeed, at that point, the objective function value is 0. Okay? Now, this is a maximization problem. So what should I be looking for? So I should be looking for a non-basic variable with a negative coefficient, right, in row 0. Okay? Because I know that increasing such a variable will also increase the value of z. And this is a maximization problem, so I want to increase the value of c. Note that in this case, I have two choices, right? I can increase the value of x1, or I can increase the value of x2 as well. Okay? And either one of them will increase the value of z, basically. Okay? So once again, just like we did earlier, if I increase x1 by 1 unit, then z will also increase by 1 unit, right? Okay? But if I increase x2 by 1 unit, then z increases by 2 units. So it seems like, x2 is a better choice. So that's exactly what I'm going to do. I'm going to try to enter x2. So next I need to determine the leaving variable. So which variable will be the leaving variable? Well, I'm going to do a minimum ratio test. What's the ratio for row 1? Well, there's no ratio because this entry is not positive, basically, right? So as a result, there's no ratio here. What about row 2? Well, the same reason. So since this entry is not positive, there's no ratio here as well. Well, there's no leaving variable, right? Now, what does that mean? Now, what does the simplex method tell us? So it tells us that if I increase x2, then the value of z will increase actually, right? Okay. What does the ratio test tell us? So it tells us how much we can increase the value of x2. Okay. Now let's think about this a little bit. So basically, there's no ratio. What does that mean? So that means that I can increase the value of x2 as much as I want, and I'm not going to violate the first constraint, and I'm not going to violate the second constraint. Okay. And at the same time, I know that by increasing the value of x2, I can increase the value of c as much as I want. Okay? Well, that's it basically, right? So simplex method tells you that you can increase the value of x2 as much as you want, and you're still going to be feasible. You're still going to be in the feasible region. So that tells you that the problem is unbounded. Okay? Let me go back to the picture again. So essentially what we're doing is the following. So we're trying to increase the value of x2, so which means that we want to move in this direction. Okay? Starting from the origin. But the problem is that, so I can move in this direction as much as I want, right? So as a result, there's nothing that stops me from going in this direction. Okay? And, rightfully, basically, simplex method tells us that, well, you can increase x2 as much as you want, okay? In which case, you're going to improve the objective function value as much as you want, and you will never leave the feasible region. Okay? Well, that exactly corresponds to the fact that the Alper problem is unbounded, basically, okay? So you can increase the value of z as much as you want if you go in this direction, and you will never leave the feasible region. And along this direction, you will always have better and better values of the objective function value, so that means that the problem is unbounded. So in summary, if there is an entering variable, but there is no leaving variable, then the problem is unbounded. Okay? So I'll just play the same game that I did over there. So I'm going to try to find a parametric solution. Let x2 be equal to a, where a is a non-negative number. And let me try to figure out how the values of x3 and x4 depend on the value of a, right? So from row 1, remember x1 will be 0, so x1 does not change. So how does x3 depend on x2 by row 1? So x3 will be equal to 10 plus x2 basically, right? And x2 is equal to a, so I'm going to have 10 plus a. Okay? What about row 2? So I'm going to have 2x1. Sorry, x1 does not change. So x1 is equal to 0. Well, row 2 simply tells me that x4 is equal to 40. So in other words, the value of x4 does not depend on the value of a, right? Does everybody see that? There's a 0 coefficient here, which means that by changing the value of x2 has no effect on the value of x4, basically, right? Okay? So as a result, I have the following solution. Let me write over there. So what's the value of x1? x1 is equal to 0, right? x1 is non-basic and does not change. Okay, so we decide not to increase the value of x1. What's the value of x2? Well, x2 is the entering variable, so I'm calling it a, basically. What's the value of x3 from that equation? 10 plus a. And what's the value of x4? Well, x4 is fixed at 40, right? So it's going to be equal to 40. And once again, let me write it in the previous sort of style. x1 is equal to 0, x2 is equal to a, x3 is equal to 10 plus a, and x4 is equal to 40. And let me again decompose it in two parts. So I have 0, 0, 10, 40, which is a solution corresponding to that tableau, basically, right? x1, x2 are non-basic, x3 is equal to 10, x4 is equal to 40. Plus there's a component that depends on a. So I'm going to have 0, 1, 1, and 0. All right, so now let me look at row 0. Okay. Note that the value of z also depends on the value of x2 in this case, right? If I increase the value of x2, I know that z will increase as well, right? Because of row 0. So what's that relationship? Well, x1 is equal to 0. That does not change. So z minus 2x2 will be equal to 0, basically, right? From row 0. So which implies that z is equal to 2x2. And x2 is equal to a, basically. So this implies that z will be equal to 2 times a. Now what does this mean? Well, as I increase the value of a, then the value of z will also increase, basically, right? Okay? And I know that I can increase the value of a as much as I want. Okay? So since my goal is to try to increase z as much as I can, obviously what I'm going to do is I'm going to try to make a as large as possible, basically, right? Okay? And by making a as large as possible, I'm going to make z as large as possible. Okay? And in particular, if I drive a to infinity, if I let a go to infinity, then z will also go to infinity as well. Does everybody see that? Okay? And I know that for every choice of non-negative value of a, I'm going to stay in the feasible region. So that means that I can actually find better and better solutions by making the value of a larger and larger, and the corresponding objective function value will be larger and larger, basically, right? Okay? So which means that by simply setting a to infinity, by letting a go to infinity in the limit, then I'm going to make sure that my objective function value will also go to infinity. Okay? So there's one thing that's important here. So if I look at this vector right here, so the vector that multiplies a, so this is a fixed part, basically, of my solution. Okay? And as I change a, I'm actually taking this solution and moving it in this direction, basically, in this vector. Okay, in direction of this vector. So think of this as the starting point, and this is the moving direction. Okay? So essentially, this tells you that by moving in this direction, you're going to have better and better objective function values. Okay? Let me go back to the original picture. If I look at the first two components of that vector, the vector that I circled, so it's given by 0 and 1. But 0 and 1 is exactly this vector right here, basically, right? Okay? So which means that if starting with the solution, if you go in this direction, then you will have better and better objective function values. Okay? So in other words, the simplex method actually tells you which direction to go if you want to find better and better solutions. Okay? And that's exactly that direction over there. And that has a special name. So this is called the direction of unboundedness. Now this is important because essentially the simplex method not only tells you that the problem is unbounded, but it also gives you the reason why it's unbounded. Okay? So it says it's unbounded because if you move in that direction, the objective function value will be better and better, basically. Okay? So it also gives you a reason, a proof that the problem is unbounded as well. Okay? So it just doesn't guess that the problem is unbounded, it tells you why it's unbounded in some sense. Does it make sense? So once again, if I go back to this picture, so it tells me that if I start with this solution and if I move in this direction, then I'm going to have better and better objective function values. And indeed, that means corresponding to, moving this isopropyl line in this direction. Okay? And by doing that, I will have better and better objective function values, as a result of which the problem is unbounded, basically. Okay? So in summary then, in the simplex method, so if there's an entering variable but there's no leaving variable, then the problem is unbounded. Okay? Because essentially that means that you can increase the value of the entering variable as much as you want, and you will never violate these constraints. So as a result, the problem is unbounded. Okay? And by increasing the value of that variable, the value of z will increase for a maximization problem. For a minimization problem, of course, you're going to look for a positive coefficient, okay, in row 0. But apart from that, so if there's an entering variable but there's no leaving variable, then the problem is unbounded. Is that clear? Questions? Yes?
What is the difference between the previous problem and this problem, like the simplex method? Because it's the end is the same, so how can we understand it?
That's a good question. So the question is, what's the difference between the previous one and this one? Well, there's a big difference, actually, because if I go back to the previous example, well, this was already an optimal solution, basically, okay? So there is an optimal solution in the previous example. So x4 is a non-basic variable, but its row 0 coefficient is 0. So which means that if I increase x4, the value of z will not change. Okay? So I cannot actually improve the value of z any further. I already find the optimal solution. I'm just looking for different optimal solutions. Okay? Whereas in this example, actually there is no optimal solution. That's the biggest difference. So it tells you that, so here note that the coefficient of x2 is negative. So which means that this is not optimal right now. Okay? So this is not optimal. I just realized that I can actually improve this solution. And then after doing the minimum ratio test, after realizing that there's no ratio, I realized that I can actually improve this as much as I can. Okay? So that tells me that the problem is unbounded. Okay? In the previous example, we did find the optimal solution. And we were just looking for different optimal solutions. So that's the main difference between the two. Other questions? Okay, let's take a break. We'll continue.